Today, I'm going to teach you all about gravitational waves. So what inspired me to do my paper is that sometimes when you want to learn about a new topic and you're reading a paper, you don't really understand what you're reading about, and then you have to keep going to Google to try and figure out, okay, what are they saying? And if you and after going on Google to try and figure out what they're saying, like over and over again, you eventually lose interest. So in my paper, I compiled everything that you would need to understand gravitational waves at an introductory level. So the idea of gravitational waves did not exist until Albert Einstein theorized them in 1905, which was 120 years ago. So they are a result of his theory of general relativity. So, in order to fully understand gravitational waves, there are a few things we need to know about. So, the first thing we need to know is general relativity. And general relativity, the theory of general relativity predicts that gravity is not a force, but is rather the product of the curvature of space-time and its effect on surrounding bodies. So overall, the theory of general relativity has been successful in explaining events such as the bending of light and the orbiting of planets, and it is the foundation to understand how gravitational waves are produced. The second thing we need to know is spacetime. And simply put, spacetime is the space in which time exists, but a more complicated way to say this is to say that spacetime is a combination of the three dimensions of space with the dimension of time. The third thing we need to know is gravity. So it is commonly known that gravity is caused by the attraction between masses, where, for example, we sit and stand on the earth because the earth's large mass draws us into it. So Einstein's theory of general relativity shows that gravity isn't a simple force we experience, but it is caused when a mass warps spacetime. To understand gravity and spacetime, you can think of spacetime as a trampoline and the sun as a bowling ball and the earth as a tennis ball. So basically, if the bowling ball is placed on the trampoline, then it will make a large dent in the trampoline, a large depression because of its heavy mass. And if you place a tennis ball on that same trampoline, it would also make a dent in the trampoline, but it would not be a large dent because it has a smaller mass than the bowling ball. Now, if that tennis ball were to end up in the range of the dent of the bowling ball, the tennis ball would be drawn closer to the bowling ball through the dent and it would roll like down the dent and towards the bowling ball. And that's kind of how gravity works. So the fourth and final thing we need to understand is waves. A wave is a medium that transfers energy without transferring matter, and ripples in water provide evidence that waves transfer energy but don't transfer matter. And waves create disturbances called oscillations. And for example, sound waves are created when air particles are made to vibrate. So there are many different types of waves, but the main ones are longitudinal waves, transverse waves, and electromagnetic waves. Longitudinal waves create oscillations parallel to the direction they travel in, and an example of them are sound waves. Transverse waves create oscillations perpendicular to the direction they travel in, and light waves and ripples in water are examples of transverse waves. So electromagnetic waves are waves that are made up of oscillating electric and magnetic fields, which move through space at the speed of light. And they encompass a broad spectrum known as the electromagnetic spectrum, Microwaves, visible light, and X-rays are a part of this spectrum. Finally, after learning all of that, we can now understand that a gravitational wave is a disturbance in the fabric of space-time. They are caused by massive objects spinning at high speeds. They are transverse waves. They move at the speed of light. But despite the fact that they move at the speed of light and are transverse waves, they are not electromagnetic waves because they are not created by oscillating electric and magnetic fields, but instead are created when there is a disturbance in the fabric of space-time. And also, when a gravitational wave passes through an object, it causes a dilation in the form of a stretch or a shrink. So there are many different sources of gravitational waves, but one of them is a binary. And a binary system consists of two gravitationally bound stars that orbit around a common center of mass. So this common center of mass is called the n spiral, and a few of these binaries are black hole binaries, which is just two black holes spinning together. So the gravitational waves are then created by the binary as it spins together uh, on the space trampoline and causes disturbances, which are the ripples in space-time. Another one of these sources is a supernova, and a supernova is one of the most spectacular events in the universe, in my opinion, because it just looks so beautiful, even though it is the death of a star. And there are various ways that supernova can produce gravitational waves, but one way is if the core is rotating fast enough for the star to collapse and bounce. So collapse is when a star collapses under its own gravity at the end of its cycle and turns into a neutron star or a black hole. And bounce is when a star collapses and then rebounds into a new expansion phase. So unfortunately, the required conditions only take place in a small population of stars. So the amount of gravitational waves emitted from collapse and bounce are very limited. So as I mentioned before, dilations caused by gravitational waves cannot be seen by the naked eye. So scientists built observatories to detect and measure these dilations, and the Laser Interferometer Gravitational Wave Observatory is one of these observatories, and it is a very, very important observatory because it was the first observatory and it detected gravitational waves for the first time in 2015, which proved Einstein's theory of general relativity and created the new branch of gravitational wave physics. And it is very, very sensitive and is made up of three Michelson interferometers located in Hanford, Washington, and Livingstone Parish, Louisiana. So, the future of gravitational waves. Because the topic itself is really new, there is still a lot of room for improvement. So, NASA has been working on a new gravitational wave observatory in space called LISA, or the Laser Interferometer Space Antenna, which will be able to detect gravitational waves of a longer wavelength than LIGO, which opens us up to more sources. And as I said before, waves carry information and energy without transferring matter. So scientists will be able to use this observatory to learn more about the source that emitted the waves. And another gravitational wave observatory that is being worked on is Taiji, and China is working on it right now. And it is also a space observatory like LISA, but it will specialize in detecting super and immediate black hole mergers which is basically just when two black holes come together and they release a lot of energy, which causes a disturbance in space-time and creates gravitational waves. And this will allow us to learn more about black hole mergers and black holes. So, um, key takeaways are that gravitational waves are ripples in the fabric of space-time. The waves carry energy and information from their sources. They first came up in Einstein's theory of general relativity. A few sources of gravitational waves are binaries and supernova. LIGO is the first detector. LIGO proved the existence of gravitational waves, and scientists use gravitational waves to learn more about their sources. So I hope you have learned something from this lesson and now have enough background information to maybe dive deeper into the topic of gravitational waves or to teach your friends and family what you've learned today. Thank you. Have a good rest of your day.
Thank you, Makaita, for that excellent presentation on gravity. And now we'll take questions. Anyone from the audience wants to ask a question? And while we wait for that, Makaita, so you showed that LIGO has this enormous size to detect gravitational waves. Do you happen to know why you need such long interferometers to detect the waves?
Oh, I don't really know, but I think it's to eliminate any like any issues that will come with detecting the gravitational waves.
Absolutely. Yes, you're right. Because as you pointed out, those disturbances are so tiny that measuring them is a challenge. So, exactly, you need to eliminate other noises. And Makaita, what inspired you to pick this topic?
A while ago, I did a presentation on gravitational waves with one of my friends, and I was just really irritated because I couldn't understand the research papers and all that stuff. So I just wanted to put information together so other people would be able to understand the topic.
Yeah, and this is arguably one of the most challenging topics in all of academia. How were you able to drill down and understand it better despite the technical complexity?
So if I didn't understand anything, I would watch a YouTube video, and they were really good ones. So yeah, I just used them to learn more, and then I used the information from the papers and wrote it out in my own words.
That's great. And what would you say is the most surprising thing you learned?
Mm, I guess that it took so long to detect the gravitational waves because how long did it take? Like 110 plus years? Because I thought it would take less time than that because Einstein theorized them and then I thought people would have started working on it earlier, but then it took so long.
Yes, it did. And funnily enough, I happened to be at MIT when Ray Wise, one of the um, big brains behind the experiment, got the Nobel Prize. And people did reflect on just how incredibly long it took to prove its existence. So you're right to point out that's a remarkable fact that it takes over 100 years to prove something that we know exists.
Mhm.
Great. Well, any other questions for Makaita before we move on to the next speaker? Well, if not, Makaita, thank you so much for the illuminating and thorough presentation. I know this topic, but still found it very helpful and learned a lot. So I'm sure others will share that sentiment. Thank you. And if anyone has further questions for Makaita, feel free to ask it in the chat. Thank you.
Thank you.